Okay, so I'll welcome to the fourth week of the live tutorial session for the course points at topology. So today we'll be mostly focus on the problem based on basis, subbasis, and related things to continuous function for basis and subbasis. Some of the question again will be related to the assignment 4 question, assignment 5 mostly. Okay, so let us start with the first this problem, that suppose x tau is any topological space and A is a subset of x. Then the characteristic function from x to r is defined as it takes value 1 for all the points in A, and outside of A it takes 0. Then this characteristic function is lower semi-continuous if and only if it is A is open, and it is upper semi-continuous if and only if A is closed. So any idea how to do this? Mostly it is will follow from the definition. Yeah,
I think it just apply the definition directly.
yeah. So lower a function chi A, this chi is lower semi-continuous. So then if and only if it is f inverse A infinity or like any A, so sorry, in this case not f, it is chi inverse of A infinity, this open interval is open for any A in like minus infinity less equal to A infinity. Okay, so okay, maybe we can put equal here infinity also. Infinity will mean that it is phi. Okay, so but this is like if and only so suppose this is happening for all A minus infinity, but this chi takes only value 1, 0 and 1. So if it is include, like if age less than 0, then it includes the inverse image will be whole of x. Otherwise it is like if it is something in between 0 and 1, then the inverse image will be only include A, right? So now let us just chi A inverse, just chi inverse of, let us say, A infinity, how it look like. So for different value of A, so if it is let's say A greater than 1 or greater equals to 1, then it is strictly it would not involve 0 and 1 both. So for that chi has no value there, so it will be phi. Okay, and if it is let's say 0 A, okay, greater than 1, yeah, that's also fine. So if it's strictly in between this thing, so then it will involve 1, right? So then it is A, and
I think we can include 0 to here, right?
yeah,
It's
0 also,
open-ended.
yeah, open interval, so 0 also we can include, yeah. And otherwise if it is greater than 0, sorry, less than 0, then it is all of x, right? So so x and phi always included in the topology, so they are always open as well as closed. So only thing we need to check for a, so is open, but this if and only if a is open. Okay, so similarly just upper semi-continuous, so this is part A. For part B again, chi is upper semi-continuous, if and only if chi inverse of minus infinity A, this thing is open, or again the same thing. Okay, so okay, so for this one again, this is happen if and only if chi inverse of just minus infinity A. This is again like phi if it is on the like a less equal to 0, right? Because then it is minus infinity to, so that will not include 0 or 1 both. So in this case this is phi a if it is like, okay, not a but a complement, right? So if it is include 0, so if strictly a is equal to 1, then it will include points which does not belongs to a, that means x belongs to a complement. So then chi inverse, this is a complement and this is whole of x if a is strictly greater than 1. Okay, the same thing. Then this is open, but this is open means a complement is open, because again 0 phi and x are always open, so a complement is open, but a complement is open means is closed. Okay, so that's a like easy consequence of this thing, that whenever you have this function, we'll see just later that a function is continuous if and only if it is both lower and upper semi-continuous. So in this case it is saying that for chi to be continuous, we need both a to be open as well as closed, right? So that is about our next thing, the next problem. So here I'm claiming that any function from a topological space X tau with to R with usual topology on R, it is continuous if and only if it is both lower and upper semi-continuous. Okay, so one direction is almost clear, right? The continuous, if f is continuous, then any inverse image of any open set is open. So in particular I can take the open set to be of the form minus infinity to a, that is also open, or a to infinity. In both cases they are open sets, so inverse image of them will be open. So that's that will say that continuous if continuous implies it is both lower and upper semi-continuous. So the converse thing is also almost immediate, so type that. So if is continuous, this implies if inverse a infinity and if inverse minus infinity, both are open. open for any. So that means it is exactly the thing that if it's both upper and lower semi-continuous. Okay, so for the converse thing, you have that if it's both upper lower semi-continuous, then how can you prove that if it's continuous? Okay, so then so again I have to prove that for any inverse image of any open set is open, right? So can you prove that?
By taking a suitable intersection, I think we can do it.
Yeah, so then you are saying so instead of taking the all open set, I should only focus on like open interval, right?
That one, yeah, one of the things, yeah.
Yeah, so that's also fine because okay, that is also another thing that if you show the inverse image of basic open set is open, then that will guarantee that f is continuous. That is also part of the thing because f inverse of any union, yeah, f inverse of any union is union of the individual inverse. So each of them is because any open set. So let me just write that. So prove if is continuous, prove inverse image of any basic open sets, namely the interval. They forms a basis for this usual topology R. So namely AB for any AB with A less than B. Okay, namely is open. Okay, because like this is again as any open set as AB belongs to R less than B forms a basis of U and basically f inverse of U, I can write that as an union of interval. So is f inverse of union of over some indexing set I, AI, BI, this thing, and this thing is inverse of this union is union of the inverse. So AI, BI. Now I know this inverse image of this thing is each of these thing is open, so union of arbitrary open sets, they are all again open, so finally this is open. So that's the basically reason for like like enough to show that if inverse image of basic open set, namely this interval, is open. Okay, so Okay, so now in this case here for A belongs to R with A less than B, F inverse of AB, this interval I can write as like intersection of one this right infinite set and the left infinite set. So namely this I can write as F inverse of minus infinity to B. So this cover whole this. So this is my AB. So I'm considering this and then this. So their intersection will be exactly this AB. So A infinity. Right. So and again inverse image of this intersection is also individual inverse. So F inverse of minus infinity B and intersection of minus infinity. So both of them open by our assumption that F is both upper and lower semi-continuous, so they are open, so this is open. Are open by assumption. Okay, so this proves the first part. So for the second thing, it is saying supremum of any collection of lower semi-continuous function is lower semi-continuous. So how one define a supremum of any collection? So let me first. So let consider this Fi be any collection of lower semi-continuous function okay. So now one thing to like we are considering the supremum of all of them, so one thing we have to guarantee. So again let F equal to okay, so we need this assumption actually, so forgot to mention that. Okay, so further we need to assume that this Fi family are actually uniformly bounded. That means for each so just let me write. So for further assume the family is pointwise uniformly bounded. Okay, so at least bounded above or that thing enough. So that is this Fix, this is less than some k for all I and each x belongs to let's say in the where the function are defined. So let's say they are function from x to r. So there this should happen. Then I can define a function namely the supremum. Define Fx as the supremum over all I, this Fix. Then as this each Fix is bounded by k, So maybe it is just kx is also enough. So it may depend, this k is may depends on x also, so that also I don't need for each x. Okay, kx belongs to R. So then the supremum does exist, and we define that point to be as a new function fx. Okay, so we claim that this f is also lower semi-continuous. That's what we need to prove. So if I say, like, let's see what it says, fx is less than some or is greater than k, because lower semi-continuous we have to see whether f inverse of a comma infinity is open or not. So that means what happens if I consider fx greater than some a. Okay, maybe just a. So this implies, so fx being the supremum of all these, so anything, so supremum means it is least upper bound, right? So anything lower than that, so supremum, anything smaller than the supremum, that cannot be upper bound. That's the definition of supremum, right? So anything smaller than that cannot be a like upper bound for all these fi, right? So this implies there exists some let's say I1 such that at this point the if I1 value of that thing is must be greater than a. If I1x, that must be greater than a, right? And so this again implies that this x belongs to if I1 inverse of a infinity, right? So anything x, if x belongs to f inverse a infinity, that implies, so now x belongs to f inverse a infinity implies that fx is greater than a. So from there I get that x is belongs to, if I1 a belongs to infinity, so for, let's say the indexing set is lambda. Okay, so for some I1 belongs to this indexing set. Okay, so from there we can say that if anything the converse thing is also true, right? If some I1 has value in there, so x belongs to there, then that also cannot be a like supremum of that thing. So from there also we get the converse thing also. So what we see, combining both way, that f inverse of a infinity, this thing is nothing but union over all I1. So union over I belongs to this the indexing set such that f inverse f I inverse of a infinity, right? Is this clear? So I want to show that this f is lower semi-continuous, so I have to show that this f inverse a infinity is open. So for that reason I consider a element of f inverse a infinity, and I show that this element belongs here if and only if the element belongs to some f I1 a infinity, right? For some I1 belongs to lambda. So from there we can see that this f inverse a infinity is exactly the union of all these f I inverse of a infinity. So that's what I written. So but f I inverse of a infinity, each of them, yeah.
Can you pull up the previous screen, please?
Yeah, sure.
At the bottom, the last line, but the
Yeah.
second relation.
Yeah.
Fx greater than a implies there is some I1 such that, yeah, that part.
Yeah.
Please elaborate that part.
Okay. So fx is the supremum of fix, right? So supremum, by definition of supremum, it is the least upper bound, right?
Yeah.
So I took a such that it is strictly less than that the upper bound, least upper bound. So that means that anything smaller than that thing cannot be a upper bound.
A cannot be alone. Yeah.
So that means there exists some uh, I1, so this I1 belongs to lambda, such that the functional value f I1 functional value at that point x is must be greater than a, right? That's what it means.
Because f is the supremum.
Yeah, f is the supremum, so some element should be there which is greater than a, and in this case the elements are like fi1 fix. So the supremum is over this lambda indexing set. So there exists, that's why I said there exists some I1 belongs to lambda such that if I1x is greater than A. So that means also that this A cannot be a upper bound. Yeah, so that's not an upper bounds, and like one element is greater than that thing, so the supremum is also greater than that thing. So the converse thing is saying that way, and the next thing is just this thing, that if I1x is greater than A, that means that x belongs to if I1 inverse of A infinity. Clear?
Yeah. Thank you.
Okay, so from there I wrote this thing that f inverse of A infinity is union of fi inverse of A infinity all over this. So but each of these fi inverse A infinity is open, as fi's are lower semi-continuous, continuous. So fi inverse of A infinity is open for all I belongs to this set, and A is minus infinity less equal to A less infinity. Okay, so thus f inverse A infinity, which is again union of open sets since open, and this implies f is lower semi-continuous. Okay, so similarly the third thing, that infimum of any collection of upper semi-continuous function is upper semi-continuous. The almost the same thing follows. Again you consider let's say gi, and so let gi be any collection of upper semi-continuous functions, and functions such that they're uniformly bounded below. So in that case we need uniformly bounded above because we need the supremum to be defined there. So in this case we need infimum to be defined, so we'll consider that they are uniformly bounded below. Uniformly bounded below, that is again if ix is greater than some kx for all I belongs to, okay, so this is g, sorry, gix is this is belongs to lambda and x belongs to x, the domain of common domain of each gi. Okay, so then define this gx to be again infimum over I belongs to lambda gix. So this is again well defined function from x to r because each of these thing is bounded by kx, so infimum exists, bounded below by kx, so infimum exists, and this function is well defined. So here again we need to show that this is upper semi-continuous, so we have to see what is the g inverse of minus infinity a, right? So again let's pick an element x from g inverse minus infinity a, so that means x belongs to gx is less than a, right? But gx is less than a, infimum is again greatest lower bound, so anything greater than that lower bound cannot be a lower bound, so that means there exists again some I belongs to lambda such that gix is less than a, right? So that's what it means that gix is not like that should be a, for that to be lower bound it should be gix greater than that thing for all gi. So but here this is violating, so gix is violating that thing, so gix is should be less than a, and this if and only if x belongs to gi inverse of minus infinity a or some I belongs to the indexing set lambda. So again I can write this g inverse minus infinity a as union of g inverse of minus infinity a. So this implies g inverse of minus infinity a, this is okay, and just for if I forgot to put the one more bracket because this is the interval thing and g inverse of that interval, so okay, so anyway this is union over all the gi inverse of minus infinity a for any a infinity. So this implies H open as GIs are upper semi-continuous, so that means GI inverse of minus infinity is open, so this is union of open set, so hence this is open. So this implies G is upper semi-continuous. Okay, so all the thing is clear, right? So we started with this as continuous if and only if it is both lower and upper semi-continuous. So this is particularly the case for function which maps to R, right? So in this case, so just from the previous thing we said that if the characteristic function are lower semi-continuous if and only if it is A is open, and upper semi-continuous if and only if A is closed. So if we just see from the next thing that the characteristic function are usually are not continuous unless my A is both open and closed. So other than that, any characteristic function will not be continuous. So in case it is open, it is lower semi-continuous, it is closed, then it is upper semi-continuous. And we may define this thing that collection of, you may define a collection of this characteristic function. Each of those things are always bounded by 1, right? Because each value takes, each functions take either value 0 or 1. So although the supremum will be mostly will be 1 and other this infimum will be 0, so those functions are like anyway continuous, so that is not much like the 2 and 3 much not important in that sense. But this thing is somewhat important to conclude about the characteristic function. So direct way you can always see whether it is open or not, but this is like involving the first and second thing. Okay, so then let's go to the next one. So it is again about the basis of the topology on Cn. So start with the ring of polynomials in n variable. So each element will look like some polynomial in variable x1 x2 xn, and the coefficient comes from the from complex numbers. So for each a such polynomial, you define uf to be the all points where the function is non-zero. So it is any polynomial, so it has some degree. So once you have some polynomial of degree that has root, right? So except, so uf basically is meaning somehow that this is away from the roots, all the points which are not roots of this polynomial f. Okay, then you define that to be a collection for varying f over this set A, and you need to show that that forms a basis for some topology in Cn. And in the second thing, it is in particular, if I consider this as a base for C, then the topology actually coincide with the topology, this cofinite topology. Okay, so how to prove first part? Any idea?
I think we can just apply the definition.
Yeah, so again to prove this forms a basis for some topology on Cn, we have to first prove that the union of all this collection is totally of Cn. And second thing is if I take the intersection of any two elements from here, that should for each point there should be some point of this collection which is purely contained in the intersection, right? So two parts. So first let's see that whether this Cn is union of this uf for f belongs to A. So can you guarantee that this thing? So union always contained in the Cn, that's clear. So can you show that any point, if I pick any point from Cn, then that is contained in some uf?
Yeah, I think we can just shift the polynomial by the same complex number. Example, if you pick
Okay, so shift by that polynomial, but you have to fix some polynomial, right? So
Basically, it's a shifting technique, right?
yeah, it's kind of shifting technique, but you actually don't need to get like it is all collection of all polynomials in n variables, so you can like may focus on some finitely many polynomials, and if those polynomials are like contain the all elements of Cn, you are done. You don't have to take all the union, because there are many overlapping thing anyway. So let us take this fi x1 x2 xn, this is just xi, the ith thing. Okay, so 1 is equal to I is equal to n. Then what is ufi? So where this function is taking value 0, see it is only if xi coordinate is 0, then only it is 0. All other points it is non-zero, right? So those all points lies in this uf, or indeed that is the total uf. So it is basically all c cross c cross c, except at the ith position you have c minus 0, and then remaining all are c, right? Is this clear? Because the only 0 is lies if xi coordinate is 0. Other coordinate can be anything, but only 0 this thing is there. So this is at ith place, and you just take the union over all this fi. So do you get this Cn?
Yeah.
Okay, so then do you really get that as Cn, or am I missing something? Because okay, so if I take all the coordinates to be non-zero, then that point I can't guarantee that that is lies in somewhere, right? Okay, if all the coordinates, okay, sorry, so if all the coordinates are non-zero, then that is lies in all of them, that's fine. But if all the coordinates is 0, then that point does not lie anywhere, right? So I have to only guarantee the 0 thing, or yeah, so in particular we don't need even also this xi. If I consider the 0 polynomial, then let's say okay, so I don't need actually this thing. Actually I can define constant polynomial, right? Then the inverse image is yeah, so I don't need this to be also, yeah, take just fx1 x2 xn to be a constant thing. Yeah, so then uf is already all of Cn, because it is at every point it is non-zero. So yeah, so we don't
That's why
need,
we're shifting, right?
yeah.
From 0, you're shifting to 1.
Yes, so this implies uf, this is all of Cn, so this implies indeed this is true. So first thing is satisfied. So second thing is, if you take the intersection, so for fg belongs to a, take uf intersection ug. So I have to guarantee that this is for if I pick any element from here, that should lie in again some elements of the form this uf, and that is totally contained in uf intersection ug, right? So now can you say something about this directly, this UF intersection UG?
I think by taking the common factors, something like that.
Yeah, so just if I write this this thing, okay, so uh, this thing is all points x1 through xn, such that intersection means both of f and g are non-zero there. So
Yeah, one of them is non-zero.
yeah, so non-zero, and this is also non-zero with gxn. So if I multiply them, so this is basically, I can write also as the, so UF is the just the complement of the zero elements of there, so better to see in that way. So let us take ZF to be the all x1 through xn in Cn, such that fx1 through that thing is 0. So then UF UG both are just like ZF complement and intersection ZG complement, but this thing is, I can write as ZF union ZG complement, where either of F or G vanishes. So that means exactly that it is ZFG, right? So
Yeah, yeah,
FG
Jet
equal to
F.
either F0 or G0. So this complement. So it is nothing but again UFG. So for any FG from A, if I consider UF intersection UG, that is exactly UFG. So it is, intersection itself is a point of this set. So it is clearly like forms a basis, because you need to show that if I pick any element from here, that should lie in some element of this form totally contained in UF intersection, but intersection itself is of that form, so it forms a basis. So for the second thing, from almost follow from this one, that for n equal to 1, the topology generated by this basis actually the cofinite topology. So for n equal to 1, what it happens, so it consists of all, so UF is what, UF is all points of C basically all complex number where the function value is non-zero. That means the complement of the zero set of that polynomial. But any polynomial in C has finitely many root, namely the number of root is exactly the degree of n. So the UF are exactly the complement of finite set, and you can get any complement of finite set as UF. Namely, take suppose you have C1 C2 Cn, or let's say A1 A2 An, you have n many complex number, you consider the polynomial this x minus A1 x minus A2 product of them. So exactly the zero set is exactly A1 through An. So UF, you can you this collection is exactly the all the complement of finite set, and the topology generated, that is a like that itself is closed under union, right? Because that forms a a topology. So that is a basis, and the topology generated by that will be exactly cofinite topology, right? So second thing, B. So for n equal to 1, uf equal to x belongs to C such that fx not equal to 0. So this is some complement of a1 through ak, this complement where ai's are the roots of f. Okay, so this is again by like fundamental theorem of calculus that this f has finitely many root and exactly the root is degree of f. So from there, thus uf are all f's are collection of all complement of finite sets in C as they closed under union. That we already know because cofinite topology is a topology, so and the element is exactly of that form, the complement of them is finite set. So as they closed under union, any arbitrary union, so uf belongs to A is the topology generated by itself. Okay, hence it is the cofinite topology. Okay, so hope this is fine, right? Okay, so yeah, so then let's go to the next one. So here you consider the collection all like left closed right open intervals in R, and we want to prove that this is actually forms a basis for a topology on R, and then the topology actually is finer than the usual topology on R, second part, and third is that whether it comes from any metric, because the usual topology comes from metric and it is finer than that topology. So does that also comes from some metric or not? So the first part is again easy, because what is the like union of this thing will form. So first of all, why this R will be union of all this form, so that you can take any particular thing, so like union of particular choice of the interval. So R you can write as, let's say, union over all n belongs to Z and n plus 1, right? So this union will be all of R, right? So union is contained in R, and if I took any real number, then that real number again will lie in some n comma n plus 1 interval, again follows from this Archimedean property, and from there you can see that element belongs to some of these. So R is also contained in the right side, so hence R is this thing. So this is an easy check. For the second part is if I take again intersection of any two thing, A, B, let's say, and intersection with CD, then what will be this? So there might be like 2, 3, 4, 5 cases. So let us consider. So what happens if it is phi? When it can possible, then B should be so this is A, B, C, D, say. If B is strictly less than C or even less equal to C, then it is clearly always phi, right? And if B pass over this thing, so let's say A always, so A less than B and C less than D is always satisfied, but in this case it is like this one. So the other possible cases are like A less than C, like A less than C is fine, okay. So and C is strictly less than B and this is less than D, right? So B pass over this thing, so C comes in on this side. So in this case it is clearly C comma B, right? And so even it is equal, then also fine, right? Yeah, this is also fine. And even it is equal on this side, this is also fine. So this is CB, and if it's totally content like CD, AB is already content in CD, so that is also one possible case. So it is AB if C less equal to A and B less equal to D, or the other case that A less equal to C and D less equal to B. So in that case it will be AB totally contains CD, so it is CD, and the final thing is it can be AD also, right? AD, when it is possible, AD CA, right? So C less equal to A C less equal to A is possible, right? Yeah, it goes over this one. And so do we cover all the things or we still have something? A can be greater than B and B is less equal to D. B less equal to D is there. Okay, but this is already yeah, this is not the case, so I can have D in between. So A less than D and this is less equal to B, so then it is AD. Okay, so these are all possible cases for this any ABCD. So then it in each cases this is it is of the form this thing, right? This like always contained in L. So this belongs to this L for any choice, so that again guarantees that this is a this forms a basis. Okay, so is that this is basis for some topology on R. So how do you show that this is actually finer than the usual topology? Like what you will prove to claim that?
Any basis of the usual topology can be written as a union of this kind of sets.
Yeah, exactly. So if we can write any basis element of the usual topology in as the union of these elements, then always says that those basis elements contained in the topology of this the topology generated by this basis element. So once the basis element contained in the topology, so that means that um, the topology itself contained in also the topology generated by this cell, right? So n up to so any ab for a less than b lies in the topology generated by this. Generated by L. So that means I have to write the AB as union of that thing. But if I pick any AB, this thing, so how do you write this as union of open this thing, not close. Yeah, but how do you write this as union of elements of this set?
Left closed A plus 1 by 1000 and comma B, union of
1 plus, so okay, so 1000 n may be something that is I have to like take a bit. So let's take this as k and this is closed this, so union of this set, but k cannot be, so I have to guarantee that this still forms an interval. So this a plus 1 by k should be less than b. That means I have to get this k such that 1 by k is always less than b minus a. So but this is again exist by Archimedean thing. So take k belongs to n such that b minus a times k is greater than 1. So this will imply that 1 by k is less than b minus a, and in particular it says that 1 by n is less than b minus a for all n greater or equal to k. So you take union over all those n, so take n and n greater or equal to k. So then it's clearly will be the union, because each of these set is like increasing. So for any k and k plus 1, if k plus 1 is greater than, then a plus 1 by k1 comma b, that will contain the previous one. And so it basically the limit of this thing on the left, but the limit is exactly a, and that a cannot be lie in this set because there always exists something which like which does not contain a. So from there you can actually get this open interval as the union of this thing. So this implies AB belongs to this topology generated by L. So this is the notation for my topology. So generated by L. And this implies the usual topology on R. The U is a strictly finer. So for the strictly finer part, we have to show that something is some open set is here but not content there in the usual topology. So that set is easy to find because this set of this closed A open B, this any set will not contain in U, as this element does not belongs to the usual topology of R, right? Because this for this to be open, I need this every element of this set to be interior point, but this A elements belong here, but A cannot be an interior point because any neighborhood of this A will contain some element outside of this set, right? So from there you can easily see that this cannot be an element of the usual topology due to like this thing that it comes from a metric. But so that's complete the second thing, that it is strictly finer. But what about this third part, that does it come from any metric? So any idea?
Nah.
Okay, so like what property like can you have for the metric? You can think of something like if you had some topology come from metric, then some immediate consequence you can always say. So can you at least mention one? Then we may go to something that is needed in this case. That may not work in this case, but at least we may have some idea. So one thing, so suppose
House.
if house drop, yeah, exactly. So house drop thing is always you have. Suppose you have, so that is anyway not yet defined, but I'm just saying that suppose you have A and B to a not equal point, then you can actually, that will implies that the if you these are elements of metric space, then D of AB is non-zero. In particular, this is greater than 0. So once you have this greater than 0, you now consider, so this say this as R, you consider the ball of radius R by 2 around A and B as well. So then the intersection of those two ball will be phi. So that's an like property of metric. Whenever you have metric space, there the if you have two non-equal points, then you can actually separate those points by open neighborhood of them. So that's the house drop property. So in metric space always you have that, but in this case actually this property is not violated anyway. So can you see, like if I give you two elements A not equal to B, do you have not ball but some neighborhood which do not intersect each of them? So this property is not violated. Can you see this in this topology?
Yeah. They can always be separated.
Yeah, so if I take AB, I can just take A comma something B minus A by 2, let's say. Or so in that case I'm assuming my B is greater than A. Let's say B greater than A, not equal, so either of them happen, so let's say B greater than A. So then this thing will not intersect this B minus A by 2 B, right? So this is, oh okay, so I need B to be lie here. Yeah, so you can just add one, like anything, 1. Then this is again pi. Yeah, so this property is not validated, so you have to look for something more things. So first observation that the rational number set is dense in this topology. So first thing is that Q is dense in this topology. So can you see that? So for denseness, you again have to prove that if I take any element of any real number and any neighborhood of around that should intersect a rational number.
Yeah, it also follows easily because it is finite in the usual topology, right?
Yeah, so again, yeah, finer than the usual topology, but that is not immediately guaranteed, right? Because I have to consider like I may have something around some point which is not intersect the rational, and not due to that reason, but due to the particular basic open set of this form. Like if I can show that every basic open set intersect Q, then I'm done. But not exactly due to this reason that it is finer. In the finer set, I may have something that you hope you get. So I may have some open set here which contains some point, and that open set does not intersect Q. That might happen, right?
Can you show one example too?
Yeah, so example, let's say, so I have this topology, this towel. Just consider this like union with Q complement. Okay, just okay, should I take that? Okay. Okay, intersection. So maybe just involve the complement of this Q in the as an open set. Q complement as an open set. Involve a topology where Q complement is also an open set. So namely, you consider this topology union with Q complement, but Q complement that may not be a topology, because again intersection should be lie there. So you consider all possible intersection also there. So just make that a topology, but where the Q complement is open.
But the point I was the line that I was thinking of is that since this topology is tighter than the usual topology, and Q is dense in the usual topology, so shouldn't it be dense in this topology as well?
No, that's what I'm saying. So you have to guarantee that for each point, each neighborhood, namely if you take any open set, that open set should intersect Q. That's the density, dense thing. So for Q to be dense. But I'm saying
doesn't that follow?
No, that's what I'm saying. So the topology is finer. So there is more open set than the usual thing, usual topology.
More open sets.
Yeah, there are more open sets. So I might have some open set which does not intersect Q at all.
Yeah.
So that will say that Q is not dense.
Yeah, if we can find such an open set.
Yeah. So namely, so the most example is this. You consider the discrete topology. Discrete topology is the biggest topology. Nothing, no topology can be more finer than discrete topology, right?
Yeah.
So in discrete topology, every set is open, every set is closed. So Q closure is Q itself. So that is not dense in that topology.
Yeah.
So finer will not guarantee that this is dense, but this is dense due to the basic open set of this kind. because any basic open set contains infinitely many rational points. So any basic open set intersect Q. So if I take any other open set that is union of basic open set, so they surely will intersect any open set also.
So the argument that I presented would work if it was coarser, right?
Coarser maybe coarser it may just a minute. So if I have lower list of like less, there it surely will because you have something bigger set where it is satisfied, so in the smaller set it will surely satisfied. Yeah, sure. In the coarser thing it will be the case. Yeah, sure. There it will satisfy because the given information is more open in the more open set thing. So in the lower thing it will surely intersect. Yeah. So as Q intersect any basic open set, so that is elements of this L, because they are interval anyway a comma b, so between any to a and a less than b, so between any two numbers you know that there is infinitely rational number and irrational number as well. So anyway, so so that's why Q intersect any basic open set, and so it intersect any open set as well. Okay, so this thing is one. Now if you have a dense set in a topology and the topology comes from a metric, then you actually can get a countable basis out there. So most like this is dense and Q is countable also. So you have a countable dense set, and if the topology comes from a metric, then on the topology you can actually get a countable basis. So next claim is that if towel comes from some metric, then it has a countable basis. Okay, so that again combined from this Q is dense and on metric space you have that. So how do you produce that thing? So the thing is you consider this set all. So all balls of like rational radius as well as around the rational points. So okay, let's say first of all let D be the metric and drx and drx is the ball of radius r around x. Okay, with respect to the metric. So that is basically B R X contains all point y belongs to R such that the distance between x and y is strictly less than R. Okay, so claim is that you consider all these B R Q such that R greater than 0 and this Q, these are rational number. Okay, so this is countable because you have like this R positive rational number, so anyway any subset of rational number is rational, sorry any subset of rational numbers is countable because Q is countable and Q itself is countable. So anyway it is a subset of Q cross Q and Q cross Q is countable, so this set is also countable. So is
it like better to take R equal to 1 by n, something like that one, because you just wrote R greater than 0.
but that may not work always, right? Because you have to cover all the open set. So if you just take R to be only of the form 1 by n, then anything higher radius ball you can't cover by that.
Which are greater than 1.
Yeah, greater radius ball, that how do you cover that thing? Yeah, okay.
If I took
Yeah, I understand. So that thing, yeah, that thing is possible, but okay, yeah, that thing is possible. So all rational radius you need not know, but it's fine. Just we have to prove, yeah, that is not needed all the rational thing. But anyway, so we don't need actually all like that smaller subset. Yeah, there might be more smaller set than this one, but anyway this will solve our case and it will be like bit easier to prove. But in that case actually it is I'm not said this is hard, but anyway I'm just stick to this.
Yes.
You can prove that thing. Yeah, that's fine.
Yeah, but the R that you took here is rational, right? The R that you took.
R that I took, no, R is any rational number I'm taking, not
The
less
R
than.
that you took here is a rational, right?
R is rational. R and Q both are rational.
Yeah, I got confused. Right?
Yeah, okay. So that's why okay. No, this is rational surely. Yeah. So this is greater than 0 just to this is radius, so it cannot be 0 or less than that thing. So this is greater than 0 and Q both are rational, just yeah, countable basis. So proof of this. So can you think of something? So this is countable basis. First of all, it is countable, sure. And how this is a basis for the topology.
Any set like that can be written as a union of
yeah, so
such kind of balls.
Yeah, so but any topology that is generated by some metric, so the balls of all radius they will surely form a basis, right? Because that already proved in course that any open set in a metric space you can write it as union of balls, right? Union of balls. So once you can prove that any ball, if you take any ball, that you can write as union of this rational radius ball with rational points around it, then you are done.
Yeah.
So first of all, it is countable, and let's say U is any open set in R with towel, in town basically, not in towel. Okay, now let pick an element x belongs to u. So as u is open, so there exists a neighborhood, then there exists a neighborhood. Okay, there is a neighborhood b r x contained in u, and here if I pick, okay, now I pick it. So consider r1 belongs to q such that r by 3 less than r1 less than 2r by 3, and q1 belongs to b r over 3 is fine, r over 3 x intersection q, just that. And now claim is, so clearly x belongs to the ball of radius r1 q1 as bx q1, this thing is less than r by 3 less than r1, and y belongs to b r1 q1, this thing is imply dy q1 less than r1. No, dy x is less equal to dy q1 I took, yes, q1 plus d q1x. So this is less than r1, and q1x is again less than r by 3 because q1 belongs here. So r1 is less than 2r by 3, so this is less than 2r by 3 plus r by 3, so this is r. So this implies y belongs to br x. So this ball so this implies y belongs to okay, this implies br1 q1, this implies br1 q1, this contained in brx. So thus for any x belongs to the open set u, there exists r1 greater than 0 and q1 rational number such that x belongs to br1 q1 contained in u, because this brx we started with is in u, so this contained in u. So for each element of the open set we get such element from this set brq, so that means it forms a basis. So that the equivalent condition for these two happen to be a basis, right? So that completes the claim. So is this clear now?
Yeah.
Okay. So maybe just the taking the ball, so they are that's why here I just say that there exists a neighborhood which contained in u. So in that case, that is creating a bit problem. So in the ball, you see
This
only,
was easy.
yeah. So better to just follow for general open set instead of the ball. Okay, so how much we got? So here we showed that Q is a dense set, Q is countable. So now if tau L comes from a metric, then we also showed that this is has a countable basis. So now we say that this topology can't have, actually the topology generated by this L, this cannot have a countable basis. Then we are done. Okay, so the density set is basically we indeed don't need that density coming in this proof itself, because this B R over 3x intersection Q, that is non-empty. So like this Q1 exists as Q is dense. So for that reason we only need the density of Q. Okay.
So yeah. And this one follows because was there any result like any separable metric space has a countable basis? Is it something like this?
Yeah, exactly. So any separable metric space, separable means that it has countable dense subset, and once you have countable dense subset, then that metric space is always countable basis. So that notion is again called second countability. So we are basically will contradict this fact that this if this comes from this topology comes from some metric, then it has to have a countable basis, but in this case that is not the case. So we claim that again. Next claim is the tau L can't have a countable basis. So contrary to the contrary, suppose there exists a countable basis, let's say name it as Bn, n belongs to n, and now you consider, for as it is basis, so for each x belongs to R, so therefore for each x belongs to R, there exists some bn's from here. So some bnx, so I'm denoting the x particularly for that thing, is contained in x comma x plus 1, because x comma x plus 1 is a open set, so that is always contains x, and I should always get an element from the basis set which contains this x and contained in this open set, right? Again from the basis definition. So but this bnx, note that bnx and cannot be equal to bny for x not equal to y, because this b as x not equal to y, let's say x less than y, then clearly this x comma like so for example say x less than y, then this then y does not let's say not y, then x does not belongs to this y plus 1. there, right? X does not belongs there, but X belongs to this B, Bnx, and that is contained in xx plus 1. So it has to have this bnx to be equal to y, so at least x should contain in this this set bny, but bny is contained in this set and x does not belongs there, and that the least element of this set. So anything whichever belongs to b and y, so basically I should say that x does not belongs to, let's say just say, then x does not belongs to b and y, or conversely if y less than x, then y does not belongs to b and x, as b and y contained in y plus 1 and x does not belongs there. So these two set cannot be equal. So for each x you should get a different bnx, and they are all like different for different x. So you have a uncountable family of bnx, you should have a uncountable family of bnx. So thus this bn n belongs to n can't be countable, as it contains r orth of different set. Right? So that a contradiction, which is a contradiction, so we must, so that's the thing, that it cannot have a countable basis. So from 2 and 3 we conclude that this cannot have a this cannot come from a metric, because if it is come from a metric it is countable, but from the topology itself we show that this cannot have a countable basis. So hence last 2 points.
Can you repeat the last conclusion? Thus, Bn can't be countable.
Yeah, so TL cannot be countable. So this Bn, I'm saying for each x belongs to R, I am getting a different Bnx, and this for different x, this Bnx not equal to Bny. That much is clear?
Meaning there are at least as many balls as many real numbers.
Yeah, so as many balls, like balls means in this case I'm just considering Bn's as the countable basis. So the basis element should not cannot be countable, right? This Bnx, yeah, so those Bnx actually coming from this collection only, because that I'm assuming just a basis. Just first of all, this is a basis. So from the basis thing, I'm saying that for each x there should exist an element of that basis which contain in this particular type of sets, because they are also containing x and open set. So they lies inside that. From there I'm concluding that for each x, the element that I will get from the basis, this Bn, they are all different. So I should have in the collection R orth of such elements. but we started with we started with countable many things, so that cannot happen. So this TL cannot have a countable basis. Fine.
Yeah.
Okay, so I actually wanted to discuss this one, but it's too late. I'm just maybe you just can try this thing. This thing is like very interesting one thing, that you give a topological proof of the infiniteness of primes. So one proof you might have seen always, that this prime is infinite, taking by contrapositive way. Suppose you have finitely many primes, and then from there you contradict that this cannot be the case by taking all the products of the finite number of prime plus 1. So none of the prime divides that, and so that is one proof. But this is like very good topological proof of the infiniteness of the prime. So on the Z you define a topology like this, and not topology, define a base which actually forms a base of the topology, and in that topology, like particular thing, that no finite set can be open. Okay, so then you show that actually Z minus 1 and minus 1 you can actually write as union of all those is P0. So P0 just it is PZ. So union of PZ, there is no shift, so it is union of PZ. But PZ actually you show that this is open, right? For each SAB they are open set. So each of SAB they are open. So this is open, but if the number of primes is finite, then this is finite union of that thing. And also in the B part it is saying that each member of B is also closed. So if the union is over finitely many things, so finite union of closed set again will be closed. So the complement of that thing will be open, and in this case the complement of that thing will be minus 1 1. But just from C we just show that this thing is minus 1 1, so it cannot be open. So for this to be non-closed, we need to have P to be the number of prime to be infinite.
Can you please repeat the
So just
point?
Just repeat.
Point,
So AB are easy to just show this base. It is base, and closed thing is also fine, because you just take the complement and show that is union of finitely many of them. And no finite set is open. So because if it is open, then it should have contain at least one of this SAB. So that is not the case, because this is an infinite set, and a finite set cannot contain an infinite set. So that claim that this finite set is not open. Now focus on the part D. So D, if I say, so if the number of primes is finite, then this Z minus 1 1, this is actually union over P prime. That union, but that is just PZ. Okay, I'm just writing as PZ. This is as like all that form, but this is just P times Z. Okay. Okay, so now if then this is closed, that's the main thing. So if the union is over finitely many points, then PZ is closed as each PZ, which is just the set P0. So by that thing is by B. By B. So this implies its complement. So its complements mean Z minus this thing. So that thing is minus 1 1 is open. but that is again a contradiction to
C is contradicted.
Yeah, this is a contradiction to C. So this implies you must have the number of primes which infinite.
This is a very nice proof.
Yes.
Of topology in number 2.
Yeah. Okay, so
do you do you have more problems in your slide? I mean, if
actually I have 4 more, but I'm just go over that quickly and maybe you can try them. Anyway, I'll share the slides, retain the solution. Okay, so just for the 6 I have these are like later thing are mostly easy. So suppose you have two topology tau and tau prime on X, where tau prime is strictly finer than tau. So what can you say about the corresponding subspace topologies on the subset Y of X? So anything in mind?
I think they will also be strictly finer, one of them.
And strictly, will it follow strictly?
May not be, because there has to be a catch.
Yeah. So that's the thing. So it may not be, it surely either will be equal to, like either equal or finer, but it always need not be strictly finer. So that's the thing, that it need not be always strictly finer. So you can just directly construct some pick some X to be finite set, let's say ABC, take your Y to be AB, say okay, I may need some more element AB. Y, then you define your topology tau and tau prime such that where after like this topology you also have discussed previously, like just phi A B AB and the set whole X, and just in tau prime you defined one more set than this one, namely ABC. Phi A, okay, D I don't need anyways, fine. Okay, not AB, it is AB, AB. Okay, ABC maybe, then ABCD all content. Okay, no, I don't need this one. Yeah, just that's I need X, and here you put one more set ABC, C and X. Clearly tau prime is strictly finer than tau, but if you restrict both your tau and tau prime to Y, then here it is just all of these thing except this X, it is Y. So it is phi A AB itself, because that is Y in this case. And in this case also, if you intersect each set with Y, you will get the same topology, right? And both of them are topology, by the way, first of all. So this is one case where the topology is not strictly finer, but it is indeed equal. Okay, so next, yeah.
Did you write a CB? I mean, like tau prime, the third element, tau prime.
Third element is A, AB, and then ABC.
AB and ABC.
Yeah.
So if you intersect tau with AB, then we get phi AB. You're missing one element, I think.
Yeah.
AB, right?
No. In the
subspace
set,
topology.
Yeah, in the subset Y, what can be, so it is just when I'm intersecting with this set, it is A, intersecting this is just Y. After C or X, it is indeed AB itself, right? This set are strictly again contains Y, so intersection is still this is Y. y intersection this set is y, this set is also y.
Yeah, but what about tau and the subspace of tau y? Not the tau prime y, but tau y.
Yeah, tau y is also in this case till this point y, this is just y. So intersection with this is first will give you this one, second is y, and x intersection y is again y.
Actually, you wrote A, V. I couldn't see the A. It was very small.
Okay. Okay, yeah. No. I later included this. Yeah, that's why it is. Yeah. No, it is not V. Yeah.
No, it's clear.
Otherwise, yeah. Because
yeah, now it's clear.
Yeah. Otherwise, that will not be topology, right? Because union should be there. Yeah. Okay.
Now, so you use the same technique from last class, right?
Yeah. The same.
Yeah. By making bigger and bigger open sets.
Yes. So that is also another thing, I think, in the next question probably. Oh, that I haven't included. Okay, that I could include. I can just show you. So the similar question is, if you have a like nested sequence of subsets, then can you say that like, okay, so just let me write. So suppose you have a nested sequence of subset an such that union of an is whole of your x. Okay, then this an always forms a base, right? Base of a topology.
Yeah.
Nested means either you have an content in n plus 1 or n plus 1 content in 1 an. So in any case, the intersection of anything is lies in that set itself. So it follows like first condition already given, second thing is comes from the nested thing. So in this collection always forms a basis of some topology, and the topology actually exactly will be this an set already, because if you take any arbitrary union, so that is again a elements of this set only. So basically the topology again generated by this thing is again the same as this collection. So that is like one small observation. And another thing, if you even start with this an as subbasis, then also the topology you get exactly the same as the your this basis open set or subbasic open sets. They are the only open set. So basically you can't get anything smaller than that to generate that topology. So that is a like special case of this thing, that if you have this kind of topology, you can actually generate this type of topology by anything smaller collection. Okay, so
this is the smallest collection
that can generate this topology.
So will the subbasis and basis coincide for this topology?
Yeah, basis and subbasis will coincide in this case. Yes.
Yeah, they are the same, right?
Yeah, they are the same. Yes. So this is kind of again related to locally finite collection. So suppose you have topological space X with Y as subspace with subspace topology, and a locally finite collection of sets in Y is given. So can you get always a locally finite collection on X which actually contain this finite collection given collection A?
Be a local finite collection of sets in Y. Containing, what is it? Containing A or?
Containing A means you may have some bigger finitely locally finite collection inside X, but that also include the element of this A. Because locally finite means if you have subset sequence of subset of collection of subsets inside Y, right? here when I'm saying A is locally finite collection set in Y, so each of them are subset of Y, but in locally finite collection in X means you can consider a subset of X also, but that collection I'm saying contains this finite collection. Is it possible to think? So in particular you can just say that this locally finite collection whether locally finite in X or not, so without like involving anything new. So locally finite
should be locally finite. The collection A is locally finite at each point of Y, right?
Yeah, each point of Y.
So you're asking if we can have like probably bigger collection than this one, which might be locally. I think that answer is no.
Yeah. So do you have example?
I don't have an example. I feel like it should be no because if we extend it, then X could be something much bigger, and we might not have a local collection.
Yes. So the intuition is correct. So basically you can take your X to be called R and Y to be, let's say, open 0 1, and here you can consider the, so this collection, yeah, this will work. So in this case just if I take any neighborhood around this thing, so that should also have length 1. So there exists a neighborhood, so here there can't exist any neighborhood, but in this case we can consider. So if it is belongs something inside, I can just take the corresponding neighborhood in that thing. If it is lie already inside this one of this thing, then I will consider that neighborhood. Otherwise I can just take like this thing. So in particular if I have of the form 1 by n, then I can take 1 by n plus 1 by 2 into n into n plus 1 and 1 by n minus 2 into n into n plus 1. Yeah, this collection, this open set. So this will intersect only two things. So anything here will have always finite intersection with any open neighborhood of this thing, but this is not locally finite in R. Yeah, sure.
To make we can make 0 a problematic point, right?
Yeah,
just
0
like
is
how 1 was.
Yeah, 0 is the only problematic point.
Yes, for example, by taking a minus n comma 0 included, that collection, right? That would be a problematic point. And extending A.
So minus n comma 0.
Yeah, if we take A, the collection A union minus n comma close 0.
Yeah. Close 0.
That would not be. Yeah. So that would be problematic at 0 always, right?
Yeah. So even this collection is also not again the finite. That's what I'm saying.
Not locally finite.
Yeah, not A is also not locally finite, right? You don't have to extend also it, because by the locally finite thing you have for each point there exists a neighborhood which intersect finitely many points of that set. There exists a point. There exists a neighborhood.
Locally finite.
Locally finite means
finitely many.
Yeah, so there exists a neighborhood which intersect finitely many points of that collection. So in that case I'm saying 0 belongs to R, and any neighborhood of that thing will intersect infinitely many points of A.
Yeah. Infinitely many members of this collection.
Yes. So it cannot be locally finite. But in the Y case it is, because 0 is not there. So anything greater than 0 you can always have a number such that this k is less than 1 by n basically. this k is k is greater than 1 by n. So k lies on the left, so you have this. Okay, so I miswrote this thing. This is n plus 1 comma n, not, yeah, this is n plus 1 comma n.
Yeah, this should be on the
yeah, so there exists something so which lies outside of this thing, so it k can lies only, there exists a neighborhood only this thing. You take 1 by 1 by n, 1 by n minus 1, this thing. So you can take k to be that neighborhood of you can take the neighborhood of k to be this thing, so that will intersect only one point of that thing. So that's why 0 is not there in that space itself, so that's why it is locally finite there. But for this collection it is not, because 0 lies in R. Yeah.
The idea that we just used to show that 0 is a probability point. Can you please tell me again later, because the definition that I learned, I mean, like from the class, I mean from Sanskrit science class, is a collection is not locally finite. I mean, it's locally finite at X if a finite collection of the family intersects X. Is it correct? I might be remembering wrong. It's check.
Yeah, so a family we say is locally finite at a point X if there exists the neighborhood thing is there, right? If there exists a neighborhood U of X in X such that U intersect only finitely many members of A.
Okay.
So the neighborhood thing is there, not like point for point. The point may lie in one thing, because 0 in this case, C 0 does not contain in any of this set, but the neighborhood thing is mainly there. So you can say that 0 does not belongs in the collection A, so it does not intersect any of the set, so it is locally finite by your definition, right?
Yeah. But it is not.
Yeah, so it is not. So neighborhood things would be there. So neighborhood should intersect finitely many elements. So another two thing actually I had. One I just said. Another thing is just again a function is continuous if and only if the inverse image of subbasic open set is open also. Like instead of taking basic open set, you can also check for subbasic open set. Highlight them that you can use for the checking of continuity or openness, just to check the continuity or openness on the basic open set is enough. Okay, so that's I all had actually. So